In our notes from last time, we were working with our a times b to the x formula mostly. It started off with some of those cooling problems where you had to add or subtract a c value to it at the end, but it was still our a times b to the x. So now we're going to switch and do some financial problems, in which case you have two different formulas to use when you deal with that kind of problem. Both of these you need to memorize. They are not given to you. So the first one, or actually both of them, that capital letter P, that stands for the principal value. So whatever it is that you're starting with, so you're investing like $1,000, $1,000 would be your principal value. Amount on interest on a loan, or the amount you take out on a loan would be your principal value. It's whatever that starting amount is. Rate is always a percentage, but we want to use the decimal form of it. So we listen to Beyonce and we go to the left with our decimal always. And then T is the number of years that the scenario is looking at. A of T is whatever your new amount is. That's generally what we're looking for until we get to Unit 6 after vacation, which we will then have the new amount, trying to figure out how long it takes for that to happen. And then N is the number of compoundings. So with interest, they have different time frames that they do for compoundings. Semi-annually means that you get interest twice a year. They pay you interest twice a year, every 6 months. They have quarterly, which means you would get interest 4 times a year, so every 3 months they would calculate your interest. Weekly would be 52 times a year, not 50, 52. Monthly would be how many times a year? Nice. And daily, 365. Yes, in leap years they do actually use 366, but all of our problems will deal with 365. So we'll always be using 365. So then if they tell you that your investment is compounded continuously, those are the two key words to look for. That's when you use this formula instead, P times E to the RT. E is just simply that E that we talked about a couple of days ago. It's that letter just exists naturally in our world, 2.71 approximately. You use the button on your calculator for it. There's nothing to plug in for E. E is its own thing, just like pi is its own thing. So let's take a look at a couple of examples here. So we have Jose invest $500 at a bank offering 7.25% compounded quarterly. Find the amount of the investment at the end of 5 years if he leaves it untouched. Then they want us to change it and suppose that the amount is compounded weekly instead. Then they want to figure out how much money is at the end of 5 years. So first we'll rewrite our formula. I recommend rewriting it every time you go to use it because that's what's going to help commit it to your memory. Writing something 17 times helps commit it to memory. So what is our principal value? How much did he invest? $500. What is his interest rate as a decimal? 0.0725. And it's compounded quarterly, so his N is a 4. So the rate gets divided by the 4. And then in our exponent, it's 4 times the amount of years, which is 5. So 4 times 5. So all you have to do now is plug and chug it into your calculator. Type it all in, get the decimal. Should hopefully get that decimal. Now with money, if they don't tell you where to round to, it's always 2 numbers after the decimal. You may see sometimes that they'll tell you to round to the nearest $100 or nearest dollar, in which case there'd be no decimals there. But if it's not stated, it's always two numbers after the decimal. All right, so let's try it again. But this time we're going to figure out how much money he would have at the end of 5 years if it was compounded weekly. So what is the only thing that'll change about our equation? No. The n. N will become what? 52. So 500 times 1 plus 0.0725 over 52 to the 52 times 5 power. And he is rolling in the money now. How much more money does he end up getting? Like $2. Which, $500 giving you a difference of $2, yeah, not a big deal. But what if you were investing like $1 million? It's going to be a lot bigger change there. We got Takima invest $500 at a bank offering 7.25% compounded continuously. So that phrase right there, compounded continuously, tells us we need to use the A equals P times E to the RT power. That compounded continuously means we're using per. So what is her principal? How much does she invest? She invests 500. E stays as E. Our interest rate is 0.0725 still. And she's going for 5 years. And go ahead, type that in your calculator. Let's see what we get. Do you guys remember where E is? Second ln. ln is the top, third one from the bottom on the left side. Yeah.
If Jose in number 1 put in $1 million, the difference would have been $4,292.
Yeah, see? Last thing for today is being able to figure out what your actual growth rate or decay rate is. So we're kind of working backwards. We're going back towards y equals a times b to the x. That was in the video from Monday. If you remember, b is figured out by either doing 1 plus your rate or 1 minus your rate, depending on if it was growth or decay. If it was growth, you did 1 plus the rate. If it was decay, it was 1 minus the rate. So anytime you're trying to figure out what your actual rate of growth or decay was, you need to look at your b values. Any b value that is greater than 1 means it was a growth. And then any one that's less than 1 means that it was a decay. So our first one there, 10 times 1.04 to the x power, that is a growth because our b value is greater than 1. What was the percent of growth, though? 4% growth. Generally, the growth ones are pretty easy to figure out. So for the decay, what you have to remember is you have to figure out how much did it go down by from 1. So for this one, it was 0.80. So as some of you have already said, this one was a 20% decay. And then number 3 would be 5% decay. The decimal form of it would have been, but it makes it, it's actually 5%. Yeah. So then looking at the next ones, these ones are a little bit different because your x your exponent there is not just x, it's something else. So we have to first manipulate it, and then we can figure out what our rate of growth or decay was. So this one, it's 1.04 to the 2x power. So what I need to figure out first is what 1.04 squared is. So use our calculators, 1.04 squared, 1.0816. So that is what our b value actually would be. It would be 1.086 to the x power. So now we can actually figure out, since it's just an exponent of x, what is our percent of growth? 8.16% growth. So you have to first fix things up so that it's just an exponent of x, and then you can actually figure out your growth or decay rate. So for this one, it's 0.80 to the negative x. I don't want negative x though, so I have to first figure out what 0.80 to the negative 1 is. So 0.80 raised to the negative 1. In your calculator, what does that give us? 1.25 to the x. So what is our growth rate here? Percent growth. So initially that one looked like it was going to be a decay, but because it was to a negative exponent, it actually switched it and made it a growth problem. Number 6, what exponent would I raise my 0.95 to? 1/4. Remember, there's a 1 in front of that x. It's being divided by 4, so 1/4. 0.95 to the 1/4 power. It's still a decay. But how much is it decaying by?
About 1.3%.
1.3%. If you weren't sure and you can't figure it out by looking at it, you could always do 1 minus whatever decimal you get. It would have given us 0.013, which is 1.3%. You could have turned this into a percent and then subtracted it from 100. You still would have gotten 1.3. So there's a couple of different ways you can figure that out. All right, next one, let's take a look at this. When you are trying to figure out, you're looking at bank accounts, trying to figure out which one's going to be best for your investment, depending on how it's compounded, it actually gives you different interest rates at the end of the year. So for this one, we have an investment with a nominal rate of 5% is compounded at different frequencies. Use the formula there to calculate the effective yearly rate to the nearest hundredth for the following. So did they actually tell us what principal value we're starting out with? No. And we don't need to know that because we are trying to figure out the effective rate. We're trying to manipulate that B value part of our equation here. So we're going to be dealing just with this. So we got 5% interest. First one we're trying to figure out for if it's compounded quarterly. We want to know how much interest we're going to end up getting by the end of the year. So first thing we're going to do is let's clean up that stuff inside the parentheses. Use your calculators to help you. 1 plus 0.05 over 4. What does that give us? So now this is kind of like the last three that we were just doing. To figure out my actual yearly rate, I got to raise that to the 4th power so that it's just a t, not a 4t. So if we raise that to the 4th power, what do we get? So to the nearest hundredth, we would be getting 5.09% interest. So not actually the 5%, you're getting a little bit more. So let's see how that changes though if it's compounded monthly instead of quarterly. So 1 plus still the same interest rate, But this time I'm going to divide it by 12 because I'm going to compound it monthly, and then I'm going to raise it to the 12t power. So again, first figure out what that decimal would be inside. 1 plus 0.05 over 12. This one's kind of a little bit longer. 1.0041666667. So now what do we do with that? Oh, we're not to the 4th this time. To the 12th this time. So we're trying to go for monthly. So to the 12th power. So what is our actual growth rate to the nearest hundredth? Ooh, close. 5.12. That 6 makes that 1 round up to a 2. So you'd get a little bit more money that way, because instead of 0.09, you get 0.12. All right, so I want you to take a minute, figure out the daily. So change your 12s to 365, see what you get. You should end up with 5.13%. So if you had to choose, which one would you obviously choose? So much stuff we could end up doing with this if we had time. But that's what you kind of want to do. Looking at bank accounts, you want to actually take what is their interest rate, how do they compound it, figure out which one's going to end up getting you the most money in the long run, that kind of good stuff. All right, let's go down to number 8. So we're going to switch it up. We're not going to be talking about finance anymore. We're switching back to population. So since we're switching back to population, that means we're switching back to our equation that we learned last time or reviewed last time, a times b to the x. So if the population is growing at a rate of 22% every 5 years, then what is the growth rate for 15 years? So again, do we actually know where the population is starting? No. Do we care where the population is starting? No. We're just trying to manipulate the growth rate. So this one is growing, which means my b value would be 1 plus my rate, so 1.22. But our exponent's going to be a little different. It's going to be the number of years divided by 5. Why would I divide it by 5? Because it's every 5 years. It's growing 22% every 5 years. So however many years they give me, I got to divide it by that 5. They, in fact, gave us, for 15 years, so we got to do 1.22 to the 15 over 5. I accidentally wrote 3 because I was thinking in my head that 15 divided by 5 was 3. So go ahead, type that in your calculator, 1.22 to the 15 over 5 or to the 3rd power. So let's go to the nearest tenth. What is our percentage? You would move that over. The 8 makes the 5 go up to a 6, so 81.6%. So what's that saying is from the start of the population, whenever they start looking at it, 15 years later, it's going to be 81.6% larger than it was at the beginning. They're not adding 81.6% each year. That's how much they've added over the course of the 15 years. So then what is the effective growth rate for 2 years? So again, I'm still going to use this. But this time it's going to be to the 2 divided by 5 power. Go ahead, use that calculator, help you out with it. So again, let's go nearest tenth. What would be our percentage? 8.3%. So from the beginning to 2 years later, the population grew by 8.3%. couple more examples. So this one, we've got the effective monthly interest rate on a bond is 0.6%. What is the annual interest rate of the bond to the nearest tenth of a percent? So each month the bond is increasing by that percent. So just like we would do with all the others, we go 2 to the left, add it to 1, and each month it's increasing by 1.006. Now again, that's each month. I want it for a whole year, so I got to raise that to the 12th power. So I'm going from 1 month to 1 whole year. So nearest tenth of a percent, what is our percent increase? 7.4%. Now if I wanted to go the other way, if I had yearly and I wanted to go down to 1 month, what would I do? 1 out of 12. Yes, good. Number 10, world oil reserves are depleting at a constant 2% per year. Determine the percent decline over the next 20 years based on this 2% decline. Be careful, round your answer to the nearest percent. So if it's depleting by 2% each year, what would our B value actually be? 0.98. Remember, you would do 1 minus your rate because it's a decay. So 1 minus the 0.02 would give us the 0.98. That's going to continue for 20 years. So 0.98 to the 20th power. But be careful though. Is that how much it actually decays by? You got to subtract this from 100. How much did it actually decay by? 33%. So the decays have that one extra step. You got to remember that's not the actual decay. You got one more thing. You got to subtract it from 100. Last one, half-life. Radioactive substances half-life is the amount of time needed for half of the substance to decay. So suppose we have a radioactive substance with a half-life of 20 years. So 20 years, it's a long time. What percent of the substance would be radioactive after 40 years? So, half-life, so our B value is 0.5. So then our exponent would be 40 divided by 20 because it's 40 years that we're looking at, but it takes 20 years for it to break down. So go ahead, type that in. What do we get? 0.25. That would be 25%. This one isn't like the last problem we did. You don't subtract it from 100 because it asked us what percent of the substance would still be radioactive, meaning what's still there. 25% of it is still there. It's not the same kind of question as the last one. B, what percent of the substance would be radioactive after 10 years? So half-life, 0.5. Our exponent would be 10 over 20, or 1/2. It's 0.7071. So to the nearest tenth, 70.7%. After 10 years, 70.7% is still radioactive. And then our last one, what is the effective rate of decay for 5 years? So again, half-life, 0.5 to the 5 over 20. So we would get that, which would be what percent? But that's not the effective rate of decay. They switched it on us. Now this one is like the oil reserves when they ask for that effective rate of decay. So it's actually 16% decay.